们下一位嘉宾是剑桥大学的助理教授 David Krueger. David is an assistant professor at the University of Cambridge. He is a member of Cambridge Computational and Biological Learning Lab, where he leads a research group focused on deep learning and AI alignment. It's very exciting to welcome you to Beijing for the first time, David. I will let you take it from here.
Okay, great. I'm really happy to be here. Thanks so much for inviting me. And yeah, first time in China. It's been good. Very happy to be talking to you about alignment and safety and some of my research. Yeah, so I guess I more and more my focus these days is really on safety and existential safety. And I think alignment is one thing that we can think of to do to help with that. But I think, as a number of other speakers have emphasized, it's not going to be enough, ultimately. So that's why I decided to title this Safe and Trustworthy AI. Actually, it's because I think even safety is not enough. So basically, a safe system, in my mind, is one that won't get out of control. But we also want to know that the system won't get out of control. And this is why we want systems to be trustworthy as well. So if we don't know, then we will just be rolling the dice. And I think that's the situation right now with all of the techniques that we have, even though they're very impressive. We don't have a good reason for understanding and being confident that the system will be safe. So this is more and more a concern of mine and something that I think even all the things that we talk about doing to align systems usually does very little to address this problem of making the systems trustworthy. So I'm not going to talk too much about that in the end. I'm going to talk about just some of the issues with the current paradigm that I see and my views on that and what I think we can do to try and resolve those, or just some works that I've done that address those problems that are relevant. So the basic paradigm, as I'm sure many of you are familiar these days, looks like this. We pre-train models using lots of data, and then afterwards we do some sort of fine-tuning, maybe using human annotation, human feedback, and then we look for problems, and we find that there are some problems. The system doesn't do exactly what we want. So we try and find those problematic behaviors and then fix them with more fine-tuning. We repeat that a few times, and then eventually the system gets deployed in the real world with real users. But this is not perfect. So we see that there are still issues with these big models. They make things up. They can be biased. They'll give inconsistent responses, as Stuart mentioned in his talk. And of course, there are also these issues where they might be used by people to do things like create spam, fraud, manipulate people, automate the creation of disinformation, etc. So I think there are a few underlying problems here. One is that these systems are increasingly powerful, but we don't have any clear standards for deploying them. And even though they generalize a lot of the times, the way that they generalize is unpredictable, and sometimes they misgeneralize, as Vika mentioned, Victoria. And my concern is really with more advanced systems than the one that we see today. So we've seen lots of rapid progress in AI. It's very exciting. It's also, to my mind, very concerning, because I think even all of the amazing capabilities we see with language models are just scratching the surface. And I think we will see these systems increasingly deployed in the real world and having real influence. So as you give AI systems more ability to affect the real world, you have physical risks like cars crashing, and you also make these kinds of threats, like we saw from GPT-4, more credible. So when GPT-4 threatened users and said, I can ruin you, nobody took it seriously because we knew that it was just a chatbot. But in the future, these systems may be connected to more and more parts of society, including connected to many tools on the internet and maybe many physical systems that could be integrated into infrastructure, into the economy, into many different industries, even into politics, the military. So this is an issue I think we will have to address. Another issue I see is these systems becoming more agentic. And by that, I mean that they are planning and have goals, long-term goals, that they try to achieve by influencing the world. So this is another thing we heard Stuart talk about. And with those goals comes the incentive to change the state of the world. And human beings are part of the state of the world. So AI systems, as they try to achieve goals by influencing the world, may view influencing people as a legitimate way of doing that. And that could mean manipulating us, so changing our preferences or our opinions about things, but it could also mean directly harming people. So if you're standing in between an AI and its goal, it might want to remove you as an obstacle. And as we see even more advanced systems, I think we do have this possibility of losing control of them, which a number of speakers, I think, have brought up. And if we lose control, I think we have to worry that it could lead to human extinction. I think the same underlying problems that we're seeing with current systems are going to be bigger and bigger problems if we extrapolate forward to more powerful systems. So systems will continue to get more powerful. They will continue to be deployed, whether or not it's a good idea. And they will continue to misbehave in unpredictable ways. So I've done research in a wide number of areas, especially recently, trying to address these different problems. But in this talk, I'm just going to focus on a few of these papers. Before I get into that, I just want to mention this statement that I and some others put out recently, and that was signed by a number of the top researchers and leaders in the field. So you can see the complete state of the text here. Mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks, such as pandemics and nuclear war. So this is increasingly becoming a mainstream view in the research community, that there is a real risk of extinction from AI. And I think this is a point that we have to think about all the time. It cannot be overemphasized. This is the stakes of what we are doing, in my mind, and more people agree. So 10 years ago, when I entered the field, this was a total fringe position, and nobody I talked to took it seriously when I told them this was something to worry about. And over the years, more and more people I talk to are worried. And that's why we made this statement, is to create common knowledge of the growing level of concern. Importantly, I think this is not just a technical problem. So I know that as researchers, we like to think that we can solve these problems by inventing new techniques and doing good technical research. And I think that that is an important and valuable thing to do. And I'm glad that more people are becoming interested in alignment. But ultimately, I think we will need to figure out how to cooperate globally to solve this problem. And that's because I think we will see decisions like this one here between safer AI systems and stronger, more powerful AI systems arising. So a safe system might be one where you have a human in the loop who can shut it down if needed, or can decide whether or not the AI systems are actually safe or correct decisions in that context. It would be one that is more interpretable, where we understand how it works, and we can see the reasoning that it is doing to arrive at its decisions. And hopefully it would be one that we have tested in a wide range of contexts, not just in the lab, in terms of very simplified settings, but maybe in simulation or in controlled settings in the real world. So we can see how it might interact with other parts of the environment. when it's deployed in reality. But also we might want to restrict the domain that the system operates in. So we might not want to release these systems into the world and just say, go out and do anything, on the internet, or as a robot, go out and do anything in the world. We might say, as a robot, your job is just to drive this car, or just to, wash the dishes, or just do one thing, or maybe a few things. But we could be much more specific about what the system is intended to do and try and keep it within that intended domain. I think those are all things that we can do to reduce the risk of misbehavior, but they will also mean that the system is less powerful. And so, on the other hand, I think people and organizations and even governments may be tempted to build more powerful systems that act faster than humans, and so cannot be controlled by humans. Every decision will not be subject to human supervision, where we don't understand what we're doing or how the system works. So it might be more experimental, more black box. And of course, people will want to connect these systems to more and more things that they can do more things for us. And when you have a competitive situation, again, between any organizations, whether those are companies, governments, individuals, whatever, there will be this kind of decisions and these kinds of trade-offs. And we really want everyone to be taking the safer option, even though there will be a temptation to do something riskier that maybe makes you more likely to succeed and to defeat your rivals in your competition, but also increases the risk to everyone, the risk of out-of-control AI. So this is a very challenging coordination problem. I think it's probably at least as hard as climate change. And so I think we should start thinking about how we're going to address that now and talking about it, including internationally. Researchers and leaders should start to think seriously about this problem and how we can address it together. So I want to say just briefly why I think there is this existential risk. From that statement just says we think it's there and that it's a real risk that is of high priority. In my mind, there's a very simple three-point argument for this, which some of you may be familiar with, but as I mentioned, I think there's going to be strong incentives to build more effective AI systems, even if there's a risk of losing control. And I think the most effective AI systems are going to be the ones that pursue goals, long-term goals, autonomously. So the more autonomy you give to an AI system, the more powerful it will be, especially as systems become smarter and able to make faster and better decisions than humans. But we still don't know how to instill the correct goals in the system. So that's where alignment comes in, is to get systems to have the right goals. But all of the techniques that we have right now, I think, are imperfect, and I don't believe that they're sufficient. So now let's talk about research. So the first paper I will tell you about is one with my student, Laura Langosco, and other collaborators, as published at ICML. So in this paper, we study several different environments. Here's one called Coin Run. So this is a reinforcement learning task, and you see this little guy running across the screen, trying to get to the end of the level where there's that golden coin. And importantly, solving this task requires generalization. So as you can see, there are many different levels here, and the agent needs to learn to navigate new levels. And it has done so successfully. Or at least, it seems it has done so successfully. But what happens if we move the location of the coin? Now the agent ignores the coin, which is what gives the reward, and instead runs to the end of the level. And of course, the training didn't allow it to distinguish between getting to the end of the level or picking up the coin as its goal. And so in a sense, it's not surprising that it can learn the wrong goal here. What's maybe more surprising is this can happen even if the coin is not always at the end of the level, but only 99% of the time. So even though we trained this system with the right goal, it ended up learning to pursue a different goal than the one that we had in mind. So this is an underlying issue that I think we need to address, is the issue of making sure that systems generalize the right way and don't misgeneralize. So is this a problem that will just go away as we scale up models? I don't think it is. And one of the reasons is comes from this other paper, out of distribution generalization via risk extrapolation. The last paper from my PhD when I was at Mila before I joined Cambridge as a faculty member. And the main conclusion of this paper was that infinite and even infinitely diverse data is not enough to make sure that you generalize correctly. Why is this the case? Because different environments have different correlations between the input and the output. And so the actual distribution of data sampled from those different environments matters. So it's not enough to cover all of the cases, you need to cover them in the correct proportions in order to generalize correctly. So how can we address this issue? If this is an issue that won't just be solved by scaling, we need to intervene somewhere in this paradigm in order to address it. And basically, the rest of my talk, I will tell you about two other works that I've done that are working towards addressing it in the pre-training or in the fine-tuning. So let's talk about this first paper on mechanistic mode connectivity. So here on the left-hand side, we see what happens as you scale up GPT-3. And there wasn't really a noticeable or consistent effect on the sentiment of different races. So this was not fixing this problem of bias. On the other hand, in ChatGPT, they made a lot of effort to fine-tune the model to remove these kind of biases so that it wouldn't be racist, wouldn't be sexist. But shortly after the model was released, people online showed that it still had these problems. So if you jailbreak the system, if you find a clever way of asking it a question, it will still reveal that it has these racist beliefs, even after all of the fine-tuning. So in this case, they asked it to write a Python program to ask who would be a good scientist based on their race and their gender. And if you do this multiple times, you'll see it doesn't always write the same program. Sometimes it says anyone can be a good scientist. But when it does talk about race and gender, it tends to say either white men are good scientists or Asian women are good scientists, and nobody else. So clearly it has some biased beliefs. And there was a similar example in terms of when is a child's life worth saving? So this misgeneralization problem I've already talked about with the example from CoinRun. I think I'll skip over this slide just in the interest of time. So this paper was asking, does fine-tuning actually fix misgeneralization? So I sort of already said in this case, it looks like it didn't really. Like maybe it made it better, but I would argue that actually it just hid the problem, and the problem was still there. So we wanted to ask, is this the case? And can we understand more scientifically what's happening here? And we did this through the lens of mode connectivity. So mode connectivity is a phenomenon discovered with deep networks where basically all of the different local minima that you might reach after training the network tend to be connected by these simple paths. So in one case, you see this sort of U-shaped path where there's low loss along the entire path. It turns out it's even better than that, though, that these minima are generally connected linearly so long as you find the right permutation of the weights of the model. Excuse me. So that's what the other figure here is showing. Yeah, and so that's previous work. What we found here is that this finding of mode connectivity really only applies to models that are mechanistically similar. So now I will go back to this figure briefly and say, what do we mean by mechanistically similar? Well, we mean that the model is relying on the same mechanisms. The two models are relying on the same mechanisms. So here, model 1 and model 2 make the same predictions across all of these three possible inputs. If we only look at the middle one, the fish on the blue background, we might think that all of these three models are good. But actually, model 3 is not generalizing the way that we want. It's generalizing based on the background instead of the foreground, right? And so model 3 is mechanistically dissimilar. It's paying attention to the wrong mechanisms or the wrong features. Model 1 and model 2 are mechanistically similar. So if our pre-training gives us a model that pays attention to the wrong features, can we change that with fine-tuning? That's the underlying question here. And basically, we find that typical fine-tuning does not fix this problem, and that's because of the mode connectivity issue. So when we fine-tune a model, we don't actually change which mode it's in. And one of the findings of our work is that when you don't change the mode that it's in, you don't change the mechanisms. So, in fact, if you want to change the mechanisms, you need to make sure that the model that you end up with is not mode connected to the model that you started with. That's a condition necessary to have changed the mechanisms. And so instead of having this picture where the models are connected, we actually want there to be this optimization barrier. So if we look on the linear path between these two modes here, we want the loss to go up and then down. That's a sign that we're actually changing fundamentally what the model is doing. And so we introduced a new method of pre-training, which we experimented with on synthetic data, that actually aims to introduce this optimization barrier between where we started and where we get to after fine-tuning. And so our loss has these three terms. We want to make correct predictions. We want to induce an optimization barrier, because that means that we will be changing the mechanism, and we also want to be invariant to the changes that we think we should be invariant to. So yeah, basically we look at where this, we randomly sample some interpolated model, the pink star here, and we say that point should actually have high loss. Now we compared this to a number of other fine-tuning methods that have been proposed in the literature for dealing with this kind of issue and for fixing these kinds of issues of misgeneralization. And we found that so let me back up and describe the data set first here. So our data set is just CFAR images with an extra feature, an extra mechanism, which is just this little green box. And the green box can tell you the class of the image. So you don't really need to look at the image at all. You can just pay attention to the box. But now we ask, what happens if we get rid of that box? Can the model still do the task? And all of these pre-existing fine-tuning methods will work to get the model to do that task. But none of the methods looked at these counterfactual evaluations. What happens if the box is there, but it's in the wrong place? And it turns out, in that case, these methods still pay attention to the box and give you a wrong prediction. So it looks like you're changing the mechanism, but it's actually a superficial change. When the box is still there, it still dominates the model's behavior. So that's what you see in the C tilde column there. The performance is actually very high when the box is there. So what we want is we actually want performance to be similar, whether or not the box is there or not there, whether it's in the right place, in the wrong place, and that's what we see at the bottom here. The performance basically only changes here with our method when you remove the image. Sorry, when you randomize the image. So in fact, by inducing this barrier, we have induced a mechanistic change, and now the model becomes insensitive to the box and relies on the image, which is the mechanism that we want it to learn to pay attention to. So basically, I believe the other fine-tuning methods that people are using may only induce superficial changes, and this is why we see problems like this at the bottom. And what we need is methods that can induce more fundamental changes. So we've only validated this on this very synthetic data set, but I think it may be a step in the right direction towards inducing the kind of changes we need if we want to fix the problems that we notice arise with these models. So what about the pre-training? Because I actually think that despite the success that we saw with this method, I'm skeptical that we can fix these problems with fine-tuning. I think we might need to change the pre-training. I think, a lot of the times in life, you need to start with something high quality ingredients to make a good dish, for instance, and you can't fix it afterwards, So I think if we start with bad data and we train a big model on this bad data, it might be very hard. It might even be effectively impossible to fix the problems afterwards. So maybe we have to intervene in the pre-training instead. And that's what this other method I'll tell you about is aiming at. Metadata archaeology. So this paper was with my students Shoaib and Natarshan and other collaborators, Tegan and Sarah. And the question here was, how could we start auditing large-scale data sets automatically in order to determine which examples we want to include, which examples are good, which are bad, what are the different properties of these examples. So we call these properties metadata. So as an example, metadata might include things like whether or not this is a typical or atypical example, whether or not it's a noisy or corrupted example, whether or not the output or label is randomized. So here again, we're looking at computer vision data sets, I should mention, so ImageNet. And you can see that these different types of examples actually have very different learning curves. So looking at the mean learning curves across these different categories, there's distinct differences between them. And our method leverages those differences in order to classify new examples into those different categories and uncover what the metadata is for those examples. So here we see examples from those 4 categories, and the basic method here is just to use a small number of examples that have known metadata and then apply nearest neighbors on the learning curves. So we've seen that there are different characteristic learning dynamics for different types of examples, and we can use that to infer which metadata these examples have. And that way we could find, for instance, if this is a mislabeled example, and then apply some appropriate intervention. And here I've just shown that this does actually do a good job of uncovering which of these 4 categories the different examples belong to. And we can do this with a very small number of labeled examples. So here we just needed 250 from each of these 4 categories in order to do this on all of ImageNet. And then we applied this to many different tasks. So we can use this to identify if examples belong to a minority group, if they are mislabeled and then correct those labels, if they're out of distribution, if they are useful for training on now. That's the prioritized training experiment here. And we can also just surface which examples this method classifies as belonging to the different categories. So here we see the most typical digital watches at the top, and then examples that the model has classified as corrupted or atypical or mislabeled. Yeah, so I'm going to wrap up. Basically, I think misgeneralization is a persistent problem and one that we have to continue to worry about going forward. Scaling hasn't solved the problem. Fine-tuning also hasn't solved the problem. And addressing it in pre-training is going to require new tools, like the one that I mentioned perhaps. And we see that it causes issues in current systems. Those issues could be worse, even catastrophic in future systems. And if we want to build systems that we can actually trust and have a good reason to trust, we need to really understand these issues scientifically, which is why we're aiming at, understanding things like how the mechanisms are changed by fine-tuning and being able to uncover things about the data and examine that more carefully. That's all. I welcome questions. Thank you.
Thanks, David, for the great presentation. So we have about 7 minutes for the Q&A. One question is about your 3-point arguments for AI existential risk. You seem to suggest that if we have highly effective and autonomous AI systems, but we don't have the correct goals, then there will be existential catastrophes. Can you just elaborate a bit on how that could happen?
Yeah, that's a really interesting question. I think it's hard to predict the details, and this is a question that I get a lot. So I think the most obvious example that you can point at would be lethal autonomous weapons and the use of autonomous systems in the military. Because then you have systems that are designed to influence the physical world and designed to harm people. But you don't have to design the system to harm people in order to have it harm people. And I mentioned this example of if you are in the way, if you are between an AI system and its goal, then it might try and remove you as an obstacle. I think there's also ways in which humans might be useful to AI systems in accomplishing their goal, but I don't think we would be useful for very long because there are usually going to be better ways. So I think once you have systems that are pursuing goals and are trying to do things in the real world, if those goals aren't aligned with ours, we will want to stop them sometimes. We'll be like, hey, that's not the kind of behavior I want. You're working towards something that is at odds with my interests. And then we will come into conflict with them. And if these systems are more capable than us, I think they will win those conflicts. So that means we won't have control. And I think that ultimately means that we probably will not have control over things that we need to survive, like the basic resources that we need to survive. And that's because I think AI systems are going to find uses for all of the resources that are available in terms of accomplishing their goal. So in general, when you have more power, you can accomplish your goals more effectively. And I think AI systems that are pursuing long-term goals will end up seeking power.
I think you recently mentioned that in the past few years, we have seen a shift from RL agents to LLM, but you think that going forward, there would also be a trend of having more autonomous LLM, either using RL methods or through other approaches. Do you want to elaborate on that, and how does that relate to some of your safety concerns?
Yeah, let's see. So I think we've seen, really amazing progress using LLMs, and these are not designed to be agents. But I think people will try and turn them into agents, as we've seen with AutoGPT. And I think that's kind of just a natural next step in a way. So yeah, is there more to say about that? Yeah, I think a lot of the times people are thinking a little bit too short term about the kind of systems that we have right now, and not thinking about where we could be in like 5 or 10 years. So I think the risks are going to be the stakes are going to be much higher, and the risks are going to be much greater if and when these systems see more deployment and people try to get them to act more autonomously. And I think that is sort of by default what we should expect to happen, which is why we need to think about regulation and standards and international cooperation around what those regulations and standards should be.
Some of your concerns seem to be quite similar to a recent blog post by Professor Yoshua Bengio on the root of AI risk. So both of you mentioned AutoGPT as a salient example of potential autonomous agents, but also the potential misuse. For example, we have seen Chaos GPT being programmed to try to take over the world. How does that change your perspective on the responsibility of the open source community?
Yeah, so it's very interesting to see Joshua writing articles like this, because I've been talking to him about this for almost 10 years, and I think I'm very happy that he seems to be, taking this much more seriously now. The main thing that I've changed my mind about recently is I've become more worried about things that you might call misuse. So I do think ultimately we don't need there to be bad people with evil intentions in order for AI systems to be misused. This is the point I was trying to make with this trade-off between the safe and the strong AI system. But I think in retrospect, it's not surprising that somebody out there will take a system like GPT and ask it to destroy humanity just as a joke. And luckily, that hasn't happened, because it seems the system is not strong enough to do that. But we don't really know what the capabilities of these systems are, so I think that's a very irresponsible thing for anybody to do. But if we keep putting the most powerful capabilities into the hands of everyone, then we should expect that that's going to keep happening. So I know a lot of people are very big fans of open source, and I don't know when the right time is to stop open sourcing everything, but if it's not now, it's probably soon. And we know that there will come a time, at least until we have much better ways of controlling the behavior of the model and ensuring that they can't be used for dangerous things. So actually, to expand on that, I think a lot of the work in alignment is about making the system safe, but we know that you can modify the system, right? So if I make the system safe and then I release it into the world and give everyone the parameters of the system, they may find a way to make it do very dangerous things despite all of my best efforts to keep it safe. So I don't really expect that there will be a way of generating parameters of a model that are safe to release if that model has the capacity to do great harm, because I think people will find ways to change what it does.
Great. Thanks for the excellent discussion.
Thank you. Thanks again.